Welcome to qnawire.
So in this question, we're thinking about a cable that's stretched between two supports, and we want to work out what this cable is going to look like if it has a uniform load along the horizontal. So let's try and work out how this works. So let's say we have a small section of this cable, which is starting off at an angle of theta and finishing off at an angle of theta plus d theta. Then we have the tension in this part is T plus dt, and the tension in this part is T, just T. And over this part of the cable, we have a load. So let's say that we have a uniform load with linear load weight density L, then the load here is going to be L dx. So let's try and work out some stuff about this. First of all, we need to note that theta is the inverse tan of dy by dx. And that means that d theta by dx is y double dashed over 1 plus y dash squared with a square root. Oh no, just straight up, just by the derivative of tan. So this is something we need to remember. Now let's have a look at horizontal balance. We have that T cos theta equals T plus dt cos theta plus d theta. So expanding this side and keeping only terms to first order in the differentials, we get T cos theta plus dt cos theta minus T d theta sine theta. And this tells us that dt cos theta equals T sine theta d theta. So dt by d theta is tan theta times t. Now we can separate variables. The integral dt over t is going to be the integral of tan theta d theta. But now let's use our expression here that theta is the inverse tan of dy by dx. So theta equals tan to the minus 1 dy by dx. And d theta is y double dashed over 1 plus y dash squared. Well, y dashed is dy by dx, y double dashed is d2y by dx squared. So we have the integral dt over t is going to be equal to the integral. Now tan theta is y dash, so we get y dash y double dashed over 1 plus y dash squared dx. So let's say that at x equals 0, we have tension T0. Then we want to find out what is the tension T of x. We're going to have the log of T of x over T naught. Now over here, this is a half of the derivative of log 1 plus y dash squared. So we get a half log 1 plus y dash squared evaluated at x over 1 plus y dash squared evaluated at 0. So that tells us that T of x is T0 root 1 plus the derivative squared at x divided by 1 plus the derivative squared at 0. So this is an important equation. Now let's have a look at the vertical balance. So the vertical balance is that T sine theta plus L dx equals T plus dt sine theta plus d theta. So what's this telling us? We have t sine theta plus L dx equals t sine theta plus dt sine theta plus t d theta cos theta. So we have L dx equals dt sine theta plus t d theta cos theta. So let's have a look at dividing by d theta. So L dx by d theta equals dt by d theta sine theta. And let's also divide by cos theta as well. Tan theta plus t. So we've divided by d theta cos theta. Actually, that means that we need to divide by cos theta here. So now let's look back up here to find dt by d theta equals t tan theta. So let's replace this with t tan theta. But remember that tan squared theta plus 1 is 1 over cos squared theta. So now let's also remember that we've got dx by d theta is 1 plus y dash squared over y double dash. So we have L over cos theta 1 plus y dash squared over y double dash equals t over cos squared theta. Now let's multiply by cos theta. Now let's remember that 1 over cos theta, so this is t times the square root of tan squared theta plus 1. So we have L times 1 plus y dash squared over y double dash equals t times the square root of y dash squared plus 1. So we have t of x equals L times the square root of y dash squared plus 1 divided by y double dashed. But now let's compare this to our equation up here. What we're going to find is, so let's substitute this in, t naught root 1 plus y dash squared and let's put a 0 here, is equal to L root 1 plus y dash squared over y double dashed. So let's divide by the square root of 1 plus y dash squared, and we get t naught over root 1 plus y naught dash squared is equal to L over y double dashed. And now we're getting somewhere because we have all constants here apart from y double dash. So y double dashed is going to be L over t naught root 1 plus y naught dashed squared. And this is, y double dash is a constant. So now we can integrate this easily. Y dashed is going to be the integral of this with respect to x. Y dashed naught plus Lx over t naught root 1 plus y naught dash squared. And now integrating one more time, we get y of x is y naught plus y dash naught x plus Lx squared over 2t naught root 1 plus y naught dashed squared. So now we can work out, so we've got something which has a span of 80 meters and a sag of 10 meters. So let's have a look at what this means. So we've got a span of 80 meters and a sag of 10 meters. So this is x equals 40, x equals minus 40, x equals 0, and the sag is 10 meters. So let's say that this is y equals 0, then this is going to be y equals 10. So what we have now is y of 0 equals 0. So that tells us that y0 equals 0. So that tells us that y of x is y dashed of 0 times x plus lx squared over 2t naught root 1 plus y naught squared. Now let's use the fact that y of 40 is 10. So y of 40 is equal to y of minus 40 is equal to 10. So if y of 40 is equal to y of minus 40, first of all, that means that y dash of 0 must be 0, because y of 40 minus y of minus 40 is going to be y dash naught of times 80, but this term is going to be the same. But this is equal to 0, so we get that y dash of 0 equals 0. So that tells us that y of x is equal to lx squared over 2t naught Now, y of 40 equals 10. And this is going to be L times 40 squared over 2. So 40 squared over 2 is 800. So we've got 800 L over T naught. So that tells us that T naught equals 80 L. Now remember, L is this loading parameter that we don't know. But what we do know is that the tension at the lowest point is 20 kilonewtons. So that tells us that T naught is 20,000 newtons. So L is that divided by 80, which is 250 newtons per meter. So now we've got our last equation. So now we just need to look back at our equation for T of x. T of x, let's look here. T of x equals L root y dash squared plus 1 over y double dashed. Well, let's evaluate this at the endpoint. So at the endpoint, so we've got y is, L over 2t naught is L over 160 L. So this is 1 over 160. So y of x is going to be x squared over 160. And this is telling us that T of x is 250 root y dash squared plus 1 over y double dashed. So let's evaluate this at x equals 40. So y dash of 40 is going to be 2 times 40 over 160. So that's 80 over 160, which is a half. Y double dashed of 40 is going to be, so we've got 2x, take another derivative of that, it's just going to give us 2 over 160. So this is 1 over 80. So that tells us that T of 40, which is the tension at the supports, is going to be 250 times the square root of a half squared plus 1 over 1/80th. So 250 times 80 times the square root of 1 plus 1/4 gives us 22,361 newtons.